So, dear student, in this lecture we will discuss what is Hardy-Weinberg law. We will discuss what is this law is. So, this law states that in a large random mating population, first condition is the population should be large and random mating should take place. The gene and genotypic frequencies remain constant from generation to generation. In the absence of migration, mutation, and selection, and genotypic frequency can be obtained by the gene frequency. So I want to prove this. How you can prove this? So we will start with consider a random mating population with two alleles. For example, we have these two alleles at a locus with their initial gene frequency, allele frequency is P and Q, such that P plus Q is equal to 1. And when random mating takes place, you all know we get three types of genotype. These are my genotypes with their proportion in the population is P to Q and R. And if we talk about the genotypic frequency, this will be equal to P square 2PQ and Q square, and again the sum of this P square plus 2PQ plus Q square will be equal to 1. Then of course we will get the individual of this type when a mating between the heterozygous is taken place. Then we will get these three types of genotype, and these are the population proportion, complete population proportion. So how you will prove that the gene and genotypic frequency remain constant generation after generation? So when a random mating take place, so I just create a Punnett square in which the male genotypes is crossed with female genotype. So suppose this is my female genotype and these are my male genotype, right? Now these are my proportions, population proportion P, 2Q and R. Similarly, for male P, 2Q and R. I am taking male and female same because I am talking about the selfing which occurs in plant. It means self-pollinated crop. It means same flower can be used male and female. So I will use these proportions. So when the mating take place between these two individuals, so of course we will get all the offspring of this type. When mating take place between capital A with capital A small a, so let us say this mating take place, then from this genotype only one gamete will be produced. Here we will get two gamete. One is capital A and one is small a, and they are fused to produce zygote. So we will get one type, and if this A is fused with this gamete, you will get another type. and their ratio is 1 is to 1 is to 1. Right? Now, this capital A is mated with capital A small a. Then we will get two types of genotype. Number two, there is another thing. Since this capital A of male is mated with the capital A small a of female, the reciprocal can also happen. I mean to say, the homozygous dominant parent can of female can cross with the heterozygous male parent. So this can happen with this and this can happen with this. So what happens? Since their initial proportions are P and 2Q, so 2PQ is the proportion of this mating. The individual produced by this mating, if capital A of male is crossed with capital A small a of female, then we will get 2PQ. Similarly, when capital A of female is crossed with capital A small a of male, I will again get 2PQ. Right? Now, if capital A of male is crossed with small a of female, means homozygous dominant of male is crossed with zygote recessive parent, then of course only one gamete is produced from male and only one gamete is produced from female because both alleles are same and their zygote will be capital A small a and all the offspring will be of say A type. So when this parent is crossed with this parent, it means PR will be the population proportion. And if we change the sex of these two parents, then I will get PQ here. Now, for this, capital A, small a of male means heterozygous male and heterozygous female. I mean to say capital A of male is crossed with the heterozygous of female. Two gametes are produced, capital A, small a, capital A and small a from both parents, and if their random assortment or random mating take place between these gametes, they will produce three types of zygote, say capital A, small a, small a. But you will get the ratio 1 is to 2 is to 1. Genotypic ratio will be 1 is to 2 is to 1. So 2Q is crossed with 2Q, so we will get 4Q square. Now third type of when the capital A small a of male is crossed with homozygous recessive of female. So again I will get two gametes from this male parent and only one gamete from this female parent, and we will produce two types of individual, that is capital A and capital small a in the ratio 1 is to 1. So its frequency becomes 2QR, and since if their parents are changed, so we will also get a frequency of say when A is mated with this, so this is 2QR. Now only one mating remaining, which is homozygous recessive in both parents. So only one zygote will be produced, gamete will be produced from male, and only one gamete produced from female, and their resulting genotype or offspring will be of AA type, and their proportion is PR. So I have completed all the matings with the help of this Punnett square. Now see, this is not AA. Actually, here we put the proportion, so it is P square. Now, first type of mating take place capital A with capital A. So we will get all dominant homozygous offspring. So if this is the only frequency, this will be attributed to this parent. So I put P square here. Then we will talk about capital A. Capital A is crossed with capital A small a. It means this capital A is crossed with this, or this capital A is crossed with this. So we will add these two frequencies from this mating. So it becomes 4PQ. Similarly, this PR resulted from capital A with small a, and this PQ is, this is again PR, sorry, this is not Q, this is PR. So twice of PR will be obtained from this matrix, the proportion. And capital A small a is crossed with capital A small a. So we have only this proportion, and this proportion 4Q is attributed. Now I just explain this 4Q, since two types of individuals are obtained. If I take this capital A, capital A, capital A, small a. So this 4PQ is divided into capital A, and capital A small a in ratio 1 is to 1. And from this mating, only one type of offspring are produced, that is capital A small a. So all the frequency is attributed or given to this individual which is produced after mating. Now this 4Q square, when capital A small a is crossed with capital A small a, so we get three types of offspring in the ratio 1 is to 2 is to 1. So this 4Q square is divided into capital A small a, and this is small a, and small a in a ratio of 1 is to 2 is to 1. Similarly, when we consider this mating, say capital A small a is crossed with small a small a. So this type of mating. So only one type of offspring will be produced, which are heterozygous. So all the frequency, no, this is nothing, and we are considering this cross, sorry. So we will get two types of offspring, capital A and small a in a ratio 1 is to 1. So this 4QR is divided into capital A and small a in ratio 1 is to 1. So 2QR is there and 2QR is there. Then last crossing, small a is crossed with small a. So only one type of individuals are produced like this, and whole the complete frequency is attributed to small a offsprings. So after assigning these proportions to these three individuals, capital A, capital A, capital A, and small a, we will find out their sum. So if you add, for example, total proportion after one generation of random mating, random mating can be obtained by just taking their sum. So p square plus 2pq plus q square plus, okay. So this is equal to p plus q whole square. Similarly, for you can say, just to see, okay, what is the proportion of capital A, small a after one generation of random mating? So I will add all these frequencies. So I will get 2pq plus 2pr plus 2q square plus 2qr. So I can take, of course, 2 from every side because all are 2, 2, 2, 2. Now PQ, now from this and from this, I can take Q common. So I can take Q common and I will left with P plus Q. So this is P plus Q. Now what remains? PR plus 2 QR. From this I can take R common. So I will get P plus Q. Okay. And if I take P plus Q common from this, so I will ultimately get 2P plus Q into Q plus R. Right. Similarly, you can get the proportion of small a, small a. If you want to find the proportion of small a, so I just add all the proportion obtained in this. So q square 2qr plus r square. So again it is q plus r whole square. Right? Now I will use my previous convention. If I put p as say p square, q as say pr, pq sorry, and r is equal to say q square, then what is the genotypic frequency of capital A, capital A? In capital A, I will get this P plus Q whole square. And I have already proved it. P plus Q. If I take P is equal to P square, small p square, and Q is equal to say PQ, and I substitute Q is equal to 1 minus P here, so I will get P square plus P into 1 minus P. So it becomes P square plus P minus P square. So this cancelled out. I mean to say this becomes your P. And if I take square of it, so the purport genotypic frequency after one generation of random mating of capital A is P square. Similarly, if you find out the genotypic frequency after substituting these, you will get the genotypic frequency of capital A, small a will be 2pq, and that of small a will be equal to q square. So what we conclude? So we start with same frequency and we reached again with same frequency. So it means population is in equilibrium. So the genotypic array after one generation of random mating, you will get p square capital A plus 2pq capital A small a plus q square small a. And if we want to find out the gametic array of offspring, then how you will find out what is the frequency of allele A? So you can find out this p square plus half of this, that is pq. And if I simplify it, I take p common, so it becomes p plus q, and p plus q is 1, so it becomes p. Similarly, the allele frequency or gene frequency of A after one generation of random mating. So you can find out again q square plus half of this pq. So I take q common, again I will get p plus q, so it is q. So if I create a gametic array in next generation, so these are the frequency of allele A and this is the frequency of allele small a. So gametic array will be p capital A plus q small a, which is exactly similar to that of initial population. It means after one generation of random mating, we obtained the same gene and genotypic frequency of three individuals. Means frequency is not changing. It means the population attains equilibrium. So from this table you can say if the gene frequency of A is P and gene frequency of small a is Q, and if they both are mated together, so after the mating you will get these proportion. And frequency of A is P, I have already computed, and frequency of small a is Q. So you will see from this above derivation. Hence, we prove that in second generation also the gene frequency and genotypic frequency are same. It means after one generation of random mating, population attained equilibrium. Now, this result is based on certain assumption. I have already explained that gene and genotypic frequency of a random mating population remain constant generation after generation in the absence of migration, mutation, and selection. So this is one of my condition. Number two, I have also stated in a random mating population, the mating between the gametes is at random. Means any gamete can form a zygote with any other gamete of female. Number three, equal number of offsprings are produced in each of the mating. So this is a very important condition, means number of offspring produced by a mating, that should be equal in each mating. So these are the three assumptions on which this Hardy-Weinberg law states that the gene and genotypic frequency remain constant after generation in the absence of mutation, migration and selection, and mating between the individual is completely random and they should produce equal number of offspring in each mating. Right? Now, what are the property of this Hardy-Weinberg equilibrium. Number one, the large random mating population is stable with respect to both gene and genotypic frequency in the absence of migration, mutation, and selection. Actually, this is the statement of the theorem. Number two, the genotypic frequency in the progeny means offspring, produced by random mating among the parents are determined solely by gene frequency among the parents. So I have proved it because these are my two parents with gene frequency P and Q, and P and Q and ratum and their genotypic frequency we can find out. If we mated A with A, so I will get P square, this is PQ, this is PQ, and this is Q square. So you will get a population like P square capital A plus 2PQ capital A small a plus Q square small a. So with the help of gene frequency, you can determine the genotypic frequency. So these are your genotypic frequency because this is genotype. These are the genotype, and this is the frequency of this genotype. This is the frequency of this genotype. This is the frequency of this genotype. So with the help of gene frequency P and Q under random mating, we can find out the genotypic frequency of all the offspring produced by this mating. Number three, a population is in Hardy-Weinberg equilibrium has following relation. Suppose this is a population which is in Hardy-Weinberg equilibrium with their genotypic frequency 2PQ and Q square, and their gene frequency is P for capital A, and gene frequency of small a is Q. Clear? If this is the genotypic frequency, gene frequency will be this. If this is the genotypic frequency, gene frequency will be P and Q. If Q is the genotypic frequency of small a, then gene frequency of Q will be Q. Then fourth one, the Hardy-Weinberg genotypic frequency are established one generation after random mating, irrespective of genotypic frequency among the parents. I have already proved it in the theorem. Number 5, the proportion of heterozygote never exceeds 0.5. Means if you take these three individuals and they are mated with each other, and we will see ultimately we will get these three types of individual, and by any means we cannot exceed the frequency of this heterozygote. So maximum value of 2q is 0.5 when it is happen. Let us say I am saying that proportion of heterozygote never exceed 0.5. So 0.5 कब होगा? It means 2pq will be equal to 0.5, or you can say 2pq will be equal to 1 by 2. The maximum value of 2q is 0.5. This will happen only when p is equal to q is equal to 1 by 2. How? If I substitute the value of q here, 2 into q, that is pq, this will be 0.5. So PQ will be equal to 1 by 4. This is only possible if P is half and Q is half. So when P and Q both are half, then it is 0.5. Now I take the square of it. Heterozygote square. So 2Q square is equal to 4PR. It means 2Q square is equal to 4PR. How? Because 2Q is taken as 2Q is taken as 4PR. So heterozygote square, these are the heterozygote square, is 4 times dominant into recessive. And you should note that to determine whether the observed number of 3 genotypes are consistent with expected number on the basis of Hardy-Weinberg law, you may use chi-square test. Kaise? How you can use that? So I elaborate here. Means these are 3 individuals which you observed in a random meeting. With their proportion, I have already say N2, N1. These are the observed number of offspring, and total is N. This total is N. Now, expected if N is my total number of individual, these are observed number. And then how you can find out the expected? I just multiply this N with the probability. So this can be, because this is the proportion NP square. So 2PQN and NQ square. And again total is N. So using observed minus expected whole square divided by expected and take their sum, you will find out the value of chi-square. And you can test the hypothesis that these are consistent with the expected frequency or not. So we will discuss this thing with the help of an example. The gene frequency of M in MN system is 0.63. Gene frequency for M. Suppose the frequency for M, you can say P is gene frequency of gene M. This comes out to be 0.63. So of course, what is the gene frequency of N? That can be obtained 1 minus 0.63. So it is 0.37, right? Because P plus Q is equal to 1. Now, what are the frequencies of M, N, and Mn types if mating is random? So when M is crossed with N, means we have two gene M and N of say female, and two genes of male M and N, they are of male. So since this is the proportion P 0.6763, sorry, and 0.37, similarly 0.67 and 0.37. So when M is crossed with M, so I will take 0.67 square, and in this case 0.67 multiplied by 0.63, sorry, this is 63, so 37, 0.63 multiplied by 0.37, and this is 0.37 whole. Now you can just M type you want to find out. So You just put these frequency here. First type of genotype we will produce from this matching is MM type. Second type of individual we will get MN, and third type we will get this. So it is say P square, this is 2PQ and this is Q square. In P square 0.63 whole square, 2PQ 2 multiplied by 0.37 and 0.63, and Q square, this is 0.37 whole square. So after simplification, you will get the gene frequency of M. M, if you square it, you will get this value. And if you square it, you will get this value. And for Mn type, you just multiply this and you will get this value. So with the help of Hardy-Weinberg law, you can find out the gene and genotypic frequency. Gene, or you can say genotypic frequency, can be determined with the help of gene frequency. Thank you.